Swayam Prabha. Digital India. Educated India.
So let's prove a small lemma first. Suppose that D A1 A2 AN is multilinear alternative function on the columns of n by n matrices. So I'm not assuming that its value on identity matrix is 1. I'm just saying that suppose we have a multilinear alternating function. Yeah. Then if some AK is 0, then D of this matrix is 0. So a matrix whose one of the column vectors is 0, then its determinant is D of A1, A2, AN is 0. Yeah. Then if I interchange kth and k plus first column, then I acquire a negative sign. Okay. So this is true for any multilinear alternative function. Multilinear alternative function will satisfy this property that if AK is 0, then its D of that matrix is 0. And if I interchange two adjacent columns, then I acquire a negative sign. Okay. And the same property holds if I interchange ith column with jth column. Okay. Then a negative sign is obtained. All right. So these three properties, they are true for any multilinear alternating function. Proof. Suppose a column vector of A is 0. Then the 0 vector can be written as 0 times AK. But multilinearity will say that this scalar 0 comes out. Okay, the scalar comes out. So therefore, 0 times this scalar has to be equal to 0. So therefore, multilinearity implies part A of the lemma, that as soon as some column vector of a matrix is 0, then D of that matrix is 0. Yeah, we only use multilinear property. Then let us look at these adjacent columns, AK and AK plus 1, and we will interchange and calculate the value of D. So just for simplicity, put AK equal to B and AK plus 1 equal to C. Yeah. Then look at the matrix where the kth column is B plus C and K plus first column is B plus C. So we have two identical columns. Yeah. When we have two identical columns, by alternating property, D of such a matrix is 0. Right. But now I will use multilinearity in the kth argument and K plus first argument, and apply this multilinear property. So first split B plus C. So that gives me this, yeah, and this. So I'm keeping B plus C fixed, but B plus C I can split as B and C and use multilinear property. Now I will use multilinear property in B plus C. So then I will get when you split this using multilinear property of B plus in the K plus first component, you will get a matrix where two column vectors are B and B. That will be 0. And when I use multilinear property here in this component, you will get D of A1, AK minus 1, C, and then C. And so that determinant that D will be 0. And so therefore, out of those four terms, using the alternating property, I just get that D, this is equal to D of A1 BC AN and D of A1 CB AN. And this is equal to 0. So that shows this property, that when I interchange two adjacent columns, then I acquire a negative sign. Okay. Now this trick can be used if the column vectors are not adjacent. Simply here I considered a matrix where the kth column is B plus C and K plus first column is B plus C. Yeah, I wanted to interchange K plus first column. I do the same thing to prove this fact. You look at a matrix where the ith column is AI plus AJ and jth column is also AI plus AJ, and then apply multilinearity, and you same trick will give you this. Okay, right? Okay. Now, with this experience, let us derive the formula for 2 by 2 matrices. 1 by 1 matrix determinant formula. You take a 1 by 1 matrix where determinant of a 1 by 1 matrix is the entry itself, and check that trivially it satisfies the three properties: alternating, multilinear, and normalization property. So determinant of 1 by 1 matrix has to be that entry itself. So let's look at a 2 by 2 matrix, and we use these three properties to show that determinant of a 2 by 2 matrix is uniquely determined, and it is the formula with which you are familiar. Okay, so let's take a 2 by 2 matrix. So there are two column vectors, and we want to calculate determinant function. This is determinant function is alternating, multilinear, normalized on 2 by 2 matrices. Then we want to show that d of xyzu is xu minus yz. So you know this formula. Now let us see how it is derived using these three properties. So what we do is look at the first column vector xz. So a1 can be written as xe1 plus ze2. E1 and E2 are the standard basis vectors. They are the standard basis vectors with two entries, and A2 has the entries as y and u. So A2 can be written as ye1 plus ue2. Okay, so I calculate the determinant function of this 2 by 2 matrix, where after writing A1 and A2, and we will use multilinear property. So d of A1 A2 is d of this and this. So there are two, it is a sum of linear combination of E1 and E2. This is another linear combination of E1 and E2. So I apply multilinear property in both the components. So I will first split ye1 plus ue2. So that is becomes ye1 and ue2. And I keep this fixed. Now I apply multilinear property on each one of these functions, and then I will get xe1 and ye1, but ze2 and ye1, that is the second term. Similarly, I apply multilinearity here, and so I get dxe1, yeah, xe1 and ue2, yeah, and then ze2 and ue2. Okay. Now look at this. Here x and y again by multilinearity can be pushed out, and I will get d of e1, but that determinant is 0 because two column vectors are equal. Okay, e1 and e1. Similarly, this is also 0 by the same reason. So I'm just left with this term and this term. So you get yz d e2 e1, xu d e1 e2. Now this is obtained from this by interchanging E1 and E2. So it acquires a negative sign. So YZ will acquire a negative sign. D of E1, E2, this by normalization property, this is equal to 1. And so this is equal to minus 1. And that shows it is XU minus YZ, DE1, E2, but DE1, E2 is XU minus YZ. So we have derived the formula for 2 by 2 matrices simply by using multilinearity, and normalization property, and alternating properties. All three properties are used to derive this formula, right? If you don't use normalization property, what it says is that any function which is multilinear and alternating on 2 by 2 matrices is equal to the usual determinant times the value of D on identity matrix. Yeah. So once I fix the value of D on identity matrix, then this multilinear alternating function is determined. It is a multiple of the usual determinant. So any alternating multilinear function will be a scalar multiple of the usual determinant function on 2 by 2 matrices, where this factor is D of E1, E2. Yeah. That's why we use the term normalization, because we declare D of E1, E2 as 1. Okay. So then we get the formula for determinant of 2 by 2 matrices. Any questions so far? Now it's clear that how to do this for 3 by 3 matrices. You can actually derive the formula for 3 by 3 matrices or 4 by 4 matrices, because I can play the same trick. If I have a n by n matrix, I will write every column as a linear combination of E1, E2, En. Yeah, every column will be written as a linear combination of E1, E2, En, and then I keep on applying the multilinearity and alternating property, and at the end I will get d of e1, e2, en times some number. That number is the determinant. Okay. So we want to prove that determinant function is uniquely determined. Okay. It's clear now. For 2 by 2 matrices, we have proved that determinant function is uniquely determined because we have found that function as a function of x, y, and zu. So for 2 by 2 matrices, it is clear now that there is only one function on the columns of a 2 by 2 matrix which is alternating multilinear and normalized. Yeah, and you with similar technique you can prove this fact for 3 by 3 matrices. Yeah, and but we want to prove this for n by n matrices, not by computation but by a concept. All right. So before we write a formula for determinant function, let us prove that no matter what formula you write, the determinant function is uniquely determined, yeah, on the space of n by n matrices. Any function which is alternating multilinear and normalized is uniquely determined. This we have proved for 2 by 2. We want to now prove it for n by n matrices. Okay. Now, to prove this, let us first prove this fact that suppose f is a multilinear alternating function. So I am using only two properties, multilinear alternating function on n by n matrices, and suppose that f on the identity matrix is 0, then f is identically 0. Now this vanishing lemma you can derive from on 2 by 2 matrices. This 2 by 2 case, what we proved was that alternating multilinear function on space of 2 by 2 matrices is xy xu minus yz times d of e1 e2. So if d of e1 e2 is 0, it will say that any alternating multilinear function is equal to 0. Okay. This now we want to prove for alternating multilinear function on the space of n by n matrices. We already know the proof for 2 by 2 matrices. Let's do that. So display the column vectors of an n by n matrix. Yeah. Then every column vector I can write as a linear combination. So if I write jth column vector, the entries of jth column vector are the aj column is a1j, a2j, a, this is a n by n matrix, so a and j. This is the jth column. So I can write the aj as a1j times e1, then a2j times e2, and a and j times en. So I express every column as a linear combination of these basic column vectors e1, e2, en. Right? Now f is multilinear. So once I write this, each column vector as a linear combination of e1, e2, en, I follow the process that I followed for 2 by 2 matrices and apply multilinear property and alternating property, and finally I will get a sum where I will have a permutation of e1, e2, en. So this e1, e2, en are coming in certain order, right? They are coming in certain order. You see, for the case of 2 by 2 matrices, yeah, they came in certain order, right? There were so many terms: xe1, ye1, ze2, ye1, right? So e1, e2, e2, e1, then e1, e1, e2, e2. So if I have these n terms, I can have this can be written in n ways. I can choose any ei here. Similarly, here I can put any ej, and so on. Okay. So when I expand, once I put each column vector as a linear combination of e1, e2, en, I can use multilinearity, and at the end I get a sum of this type. Yeah. So these entries a2, a1j, a2j, a and j, they will come out of the determinant function. Yeah, f is my multilinear alternating function. F is multilinear alternating function. These entries in the various column vectors will, by multilinear property, they will come out, and we will be left with f operating on a matrix where the column vectors are eh1, eh2, ehn, where h is some function of 1 up to n. right? Some function of 1 up to n. But by alternating property, whenever any of these column vectors are identical, f will be equal to 0 because it's an alternating function. So therefore, we can just focus on the terms which are bijections. Okay, these are bijections. So this H is a bijection of 1 to up to n. Okay, take a bijection of 1 up to n, and then I will get this sum. Okay, so this sum is over all the bijections. Okay, so f is operating on a matrix which is obtained from identity matrix by permuting the column vectors. Okay. Now we will apply alternating property, and by exchanging adjacent column vectors, I can convert this into f of E1, E2, En, and there will be some sign here. Because whenever I interchange two column vectors, I acquire a negative sign. So whenever I'm giving this bijection, h from 1 up to n to 1 up to n, then doing interchanges of column vectors certain number of times, f of eh1, eh2, ehn can be converted to plus minus f e1, e2, en. So this is, so my multilinear alternating function, this has any multilinear alternating function is looks like this. So if f of e1, e2, en is 0, then f itself is 0. Okay. So multilinear alternating function which is 0 on the identity matrix is identically a 0 function. That's what we have proved. Okay. Any questions on that? Multilinear alternating function which is 0 on the identity matrix is identically a 0 function. Okay. Now let's prove that if f is alternating multilinear function of order n and d is a determinant function of order n. So f lacks the normalization property, but d is multilinear alternating and normalized. So it's a determinant function. So I have alternating function, alternating multilinear function, and I have determinant function. Then this theorem says that this multilinear alternating function is actually a multiple of determinant function by f e1, e2, en. This we have proved for 2 by 2 case, right? For 2 by 2 case, we proved this formula that this D of A1, A2, An was the determinant of 2 by 2 matrix, and then this was F E1, E2. So this we already did for two by 2 matrices. Now we are doing it for n by n matrices, that any multilinear alternating function is actually a scalar multiple of a determinant function. Okay. So in particular, if f is also a determinant function, then this is 1, and therefore f equal to d. So this is the uniqueness theorem, that we show that any two alternating multilinear functions, they are scalar multiples of each other, and that scalar is the value of the function on identity matrix. So if both the functions are determinant function, then it forces the functions to be same, and therefore uniqueness will follow. That determinant function is unique function. Okay, let's prove the uniqueness. Okay, we want to prove that any two determinant functions are identical. Okay, so by first proving that any multilinear alternating function is a scalar multiple of determinant function. So look at f of a1 up to an, d of a1 up to n times f of e1 up to en. F is not assumed to be alternating, so f has certain value on identity matrix, and I look at this difference of these two. Okay. F is multilinear, D is multilinear, and this function is a scalar multiple of a multilinear function. You can check easily that scalar multiples of multilinear functions are multilinear. Sum of multilinear functions is multilinear. So this G is multilinear function. Okay. This G is a multilinear function. It is also alternating because f is alternating, d is alternating. So if two column vectors of A are identical, f will be 0, d will be 0, so G is also 0. Okay. So f and d are alternating multilinear, and therefore G is also alternating multilinear. But look at value of G at identity matrix. Okay, if I take the value of G at identity matrix, this is F of identity matrix minus D of identity matrix, that is 1, and this is F of identity matrix, so it is 0. So G is multilinear alternating function, and its value on the identity matrix is 0, and therefore it must be 0 function. Once it is 0 function, F is a scalar multiple of determinant function, and if F itself is determinant function, then this is 1, and therefore F will be equal to D. So uniqueness follows. Yeah, any questions? We have proved that without knowing a formula of determinant function, we have proved that it is unique simply by using the 3 properties, that any function which is alternating, multilinear, and normalized is uniquely determined, and we know its value on 2 by 2 matrices, and by same technique we can find the value on 3 by 3 matrices. So you should write down, you should derive the formula for determinant of 3 by 3 matrices using the 3 properties of determinant function. Yeah. So you see, we have some question. You are saying that F, D, and G here are functions. Wouldn't they be column vectors in n dimension? No, no. So and F is a function. F is a function from the space of n by n matrices. F denotes any field of rational numbers or real numbers or complex numbers. So F is a function. D is also a function, and therefore this is a value. This is in F. So G is also a function from the space of n by n matrices, and we are saying that G is identically 0. Okay, G is identically 0 because you can we've right we've proved that if I put E1, if I operate G on identity matrix, it is equal to 0, and it is multilinear alternating, and so G turns out to be 0 by the vanishing lemma, and that shows that F is D. So the determinant is unique. Is that fine? Okay. All right. So let's now look at the existence. We have proved uniqueness. Let's prove the existence. So setting determinant of a 1 by 1 matrix equal to A, you can check that this satisfies the 3 properties. So 1 by 1 matrices, it is easy. 2 by 2 matrices, we already proved. Determinant function is uniquely determined. It is the usual determinant of a 2 by 2 matrix. Yeah. So we are going to now apply induction on the number of rows of a square matrix to prove that determinant function exists. So we can assume existence of determinant function of order n minus 1 by n minus 1. That is, we know the determinant function on 1 by 1 matrix and 2 by 2 matrix, and you can calculate on 3 by 3 also. So assuming that we know what is determinant of a n by n minus 1 by n minus 1 or lower size matrices. Okay. And by induction, we know that it is uniquely determined. Okay. So we are applying induction on the size of the matrix. And we are saying that on up to n minus 1 by n minus 1 matrices, determinant function is determined. Okay. It is already unique, but we are saying that we know the formula already. Now we will derive a formula for determinant of n by n matrices in terms of n minus 1 by n minus 1 determinants. Okay. So let us look at Aij to be the n minus 1 by n minus 1 matrix obtained from A by deleting ith row and jth column. Yeah. So I have this n by n matrix, and I look at ith row and jth column and remove them. Once you remove them, I am left with a matrix of smaller size. It is square matrix. By induction, I know its determinant. Okay, I know the formula for its determinant. Okay. So now we will define determinant of a n by n matrix in terms of these determinants of submatrices. So this is called the expansion by the first row. Okay. We can actually choose any row or any column. So we are displaying the first row of the matrix. Okay. and then expanding using the first row. So A11, take A11 and delete this row, first row and first column. Now the matrix that I get here, submatrix, that we are calling as A11. So I know determinant of A11 by induction. So look at A11 times determinant of A11. Now we look at A12 and repeat this. Remove the first row and remove the second column. I get a submatrix of size n-1 by n-1, and I write A12 times determinant of A12. Okay, and this is alternating sign, so I get -1 to the power n plus 1 A1n determinant of A1n, and so I'm looking at this last entry in the first row, and then remove the first row and the last column. I get the submatrix A1n, and I multiply determinant of A1n with A1n and put a sign. So sign is alternating. We have plus sign here, minus sign here, and so on. Last sign will be -1 to the power n plus 1. Okay. So I'm defining a function. Okay. I'm defining a function in terms of determinants of smaller matrices of order n-1 by n-1. Okay. I want to show that this is a determinant function. Yeah, this is called the expansion by first row. You can take second row or third row or anything. Okay, and we can also take expansion by columns or rows and write down a formula which is simply looks like this. Okay, but to prove that it is determinant, what is our approach? We have proved that determinant function is unique. Okay, to show that this is determinant function, I must show that it is multilinear, alternating, and its value on identity matrix is 1. Okay, its value on identity matrix is 1. Okay. The value on identity matrix is 1. That is quite easy. So if I take identity matrix, this is like this. So we are expanding by this row. Only 1 is the non-zero entry. So there will not these things will not contribute. If I take identity matrix, these will not be there. I will just get 1 times determinant of this. But determinant of this n-1 by n-1 identity matrix is 1 by induction. Okay, so f of identity matrix is 1. That is clear. We have to prove these two properties, other two properties. So alternating property. Okay, alternating property. Suppose A has two identical columns, AJ and AJ plus 1. Yeah. So these two columns are identical, AJ and AJ plus 1. Then I want to show that its determinant, this f of this such a function, such a matrix is 0. Yeah, f of such a matrix is 0. Okay, so if I take such a matrix, let's say I have a 4 by 4 matrix, and second and third column, they are identical. Okay, then how will f of a look like? F of a will have 4 terms, right? A11, A12, A13, A14, and this second and third column are equal. I want to show that if I apply this formula, I get 0. Okay, I get 0.